let's get started. We're going to talk about Jupiter and Saturn. Anybody get started on the homework? No. You know why? Because there isn't any. That's right.
So is there no homework this week?
Right.
Okay. Like if there was, I needed to come like today to do it. Calculus.
Yes, sir.
Jupiter has that blue thing around it like Mars.
Jupiter has what around it like Mars?
You know how like on last week?
Oh, yes. I do see what you're saying. Yeah, the blue hoop. Okay, so we're going to talk about Jupiter and Saturn. What looks funny about Saturn in this picture?
It doesn't have its rings.
It doesn't have its rings. Right.
Less than paper than anyways.
No.
They're actually really big.
No, Saturn's is pretty big.
Everyone else is like paper.
Yeah. Okay, so let's talk about these things. First, just a last slide on the terrestrial planets. Make sure that you understand the processes of how the planets formed. And so I like this slide because it talks about the formation, how you got to where the planets are.
That's the plural for process?
Excuse me?
That's the plural for process?
That's
Processes?
what?
The plural for process?
Yes, it's processes.
I don't know what the process is.
Okay, and when we talk about the differences in our terrestrial planets, a very important consideration is, well, there's a couple of important things. The gases in the atmosphere make a real big difference. The fact that we have water, liquid water on the surface of the Earth, makes the Earth very different than it would be if we didn't have liquid water. Because that liquid water acts as a sink for carbon dioxide. That is, carbon dioxide gets absorbed into the water. The colder the temperature is, the more carbon dioxide it will absorb into the water. That carbon dioxide in the water then will combine with minerals like calcium or magnesium to form rock, like calcium carbonate, otherwise known as limestone, or magnesium carbonate. Magnesium carbonate and calcium carbonate together is what we call dolomite. Excuse me? Okay. So water helps to take that carbon dioxide out of the atmosphere and put it into rock, giving us less carbon dioxide in the atmosphere and a thinner atmosphere. We, of course, have an impact on carbon dioxide levels. Carbon dioxide levels are definitely going up because we do things like burn stuff. And when you burn stuff, one of the products is carbon dioxide. And animals release carbon dioxide as well. Plants do the opposite. Plants will take that carbon dioxide and use it as a fuel and help us to replace it with oxygen. So this is my favorite slide right here. Here we go. I'm learning how to deal with it when it messes up. So differences in planets, one of them is water. Where did we get our water on Earth? It's not on this slide. Where did we get our water on Earth? From comets. That's the conventional belief that the Earth wouldn't have had nearly as much water as we have now when it formed. Why? Because it was too hot where we formed to have much water condensed. Now, we can hold water now because the Earth has gotten large enough to hold on to water. But in early stages, you'd have to be able to have it condensed. Water couldn't condense this close, so we wouldn't have had much water until the Earth got reasonably large, then it could start holding on to water. So the calculations, the models say the Earth shouldn't have this much water, so where did it come from? And they believe it must have been from comets, from things that are icy bodies that came and crashed into the Earth. Now, this slide here is talking about what role sunlight plays. Clearly, Mercury is the first rock from the sun. It gets the most sunlight, then Venus, then Earth, then Mars for the terrestrial planets. And so each one getting farther away, you have less sunlight. And what time is your game today, Tiani? What time is your game today?
2.
So I thought. Notice he brought the computer today because he's going to pay really close attention to my lecture. Anyway, so sunlight really makes a difference. If the Earth was in the position of Mercury, it would be so hot that we wouldn't be holding on to our gases, right? And so Earth would lose a lot of its atmosphere. We had that Homer problem that talked about the relationship between temperature and gravity for holding on to gases. And yeah, we would still hold on to some gases, but not as much because of the higher temperature. And of course, with the gases that we'd retain, it would be hot all around, just like Venus is. If Venus were pulled out here, it'd be a little cooler.
It'll still be hot.
It would still be hot because of its runaway greenhouse effect. That's absolutely correct. But if it was pulled out here, maybe it would have gotten liquid water, and the liquid water would have helped to change its atmosphere so that Venus would be, habitable.
Or you just pelt those comets.
Yes, but being in there, it's likely to just vaporize it. So Venus, it could conceivably be habitable if it didn't have all that gas, if it had cool enough temperatures for liquid water to form. Instead of it for always, the theory is, got hit by comets, but the water was in the vapor phase, and that vapor phase was slowly lost because of the high temperatures.
That's why you have to hit a lot of comets at once.
Yes, okay. When we look at exoplanets, extrasolar planets, planets that are outside of the Milky Way, outside of the solar system, one of the things scientists look for are planets that are in the Goldilocks zone. Goldilocks zone is named because, of course, the story of Goldilocks, this porridge is too hot, this porridge is too cold, this porridge is just right. It probably still tastes like porridge, so I wouldn't eat it. This bed is too hard, this bed is too soft, this one's just right. The idea is that some planets are going to be too close to their star, too hot. Can't have life there, can't have liquid water, Some are too far away, can't have life there because you can't have liquid water because they freeze. So, evaporates too close, freezes too far. That Goldilocks zone is the region where the temperatures are appropriate to have liquid water. And so scientists look for planets that their distance from the stars, and of course, how much radiation the stars put off affects this, makes it so that you can have liquid water on the surface, and then they consider that's where, if we're going to find life, we're more likely to find it. Notice there's some other things here. The role of sunlight is excellent. Just another problem. Okay, when this happens, I've learned my trick. Close it. That didn't close it. I'm failing most miserably. And then reopen it, and it tends to work again. Okay, so the role of sunlight is talking about this. But notice that Venus receives 1/4 of the energy that Mercury does, just because it's farther away. And if you have an eccentric orbit, such as in a Homer problem, you looked at Mars with its eccentricity that makes it so sometimes its nearest approach is almost half the distance of its maximum nearest approach. And so when it's closer, you're going to have more heating. Very important, the axial tilt makes a difference. The Earth is tilted 23.5 degrees, Mars about 24 degrees. Similar axial tilts. Those, of course, are what causes the seasons. Now let's go to the outer planets. The primary difference between the inner and outer planets is that of size. The outer planets are much bigger, much more massive. And scientists have come to the conclusion that just has to do with the temperature. The farther you are from the sun, the lower the temperature. And we already saw we had a slide that showed the condensation temperatures for different elements. And if you're out beyond the temperature where you can have condensation of things like water and methane, ammonia, then those things will form part of your planet right from the beginning. And so the place where it gets cool enough that we can have those things condensed, we call the frost line. So the frost line is a distance away from the sun, where it's believed that during the beginning of the solar system, you could have these so-called volatiles condense together. And so since they can condense out there, you have a much larger array of gases that you can grab onto. And of course, hydrogen being the most prolific gas in our solar system, indeed in our universe, you can start holding on to this hydrogen, so you have just so much more you can grab onto that the little protoplanets and planetesimals that formed out there were able to grow to immense sizes much more rapidly. And they have much lower densities because they're holding on to materials that tend to have lower density. So the frost line is basically the separatrix between the terrestrial planets and the gas giants. Now, some people use like gas giants and frost giants. They have some different names for them, you know. When you talk about the frost giants, then you can ask the question, which I have on a...
Are they from Jotunheim?
No, where are the frost giants?
Jotunheim.
Yeah, no, well, yes, but I'm talking in reality.
I mean, like, you just gotta look at the tree Interstellar, and you can find the frost giant planet.
Yeah.
Apparently Jotunheim was...
These here, oops, I'm in black.
It wasn't. You're right.
These here are your frost giants. So the frost giants are the two outermost planets. So if I ask you in this class where are the frost giants, that's what I'm going to expect you to say.
You will be, because it's going to be on the test. That's next week.
Probably not on the test, but
We get twice a week for you.
Next week. And so that means group, we have to meet to, do our presentation.
it's a good call there, Alden.
Because you asked where are the frost giants, not who are the frost giants.
That's right, I swear. Okay, so let's go on. A very important thing here. These outer planets don't have a surface. Now, that's a little confusing because we have a surface to the Earth. I can walk out there in the dirt and I'm walking on the surface of the Earth. These planets don't have a surface, but if you look at those pictures, doesn't it look like it has a surface?
Yes.
Yes, it does. The sun looks like it has a surface too, but it doesn't have a surface either. What you have is gas that gets thicker and thicker and thicker. And when it gets to a certain thickness, it starts to be not transparent anymore. It starts to be something that's reflecting enough light that we see that reflection and we think of it as a surface.
So if we flew into it and stand under pressure and everything, would we go right through it?
No, we would not go right through it. Because as you go in, the pressure gets bigger and bigger. And so while you never would splash, you would never say, ooh, I was in gas and splash. Now I'm in liquid. It gets thicker to the point where you'd say, this is no gas, this is a fluid. Or, well, it's a liquid. Fluids are gases and liquids. So it comes to a point where it clearly is liquid, but you never have a transition from gas to liquid. And so, I mean, it's kind of odd because that's not what water does at atmospheric pressure. So you can't experience that
Unless
effect.
you actually go there.
Well, you can do things like you can heat up water. You can take water and you can take water and first you lower the pressure and then you increase the temperature I said it wrong. Take water, increase the pressure, then lower the temperature, then lower the pressure, and I still said one of them wrong. Increase pressure, increase temperature, lower pressure, lower temperature. That was the correct option. And you will clearly go from liquid to gas without ever having a transition. So you can do it on Earth, but you have to be able to control the temperature and pressure. You can't just say, the weather today is going to transition. So they don't have any surfaces, but gases turn into liquids, and eventually you get a metallic hydrogen, and then you do have in the core a solid rock. So you do have a solid surface there in the core. But nobody thinks of that solid rock in the center as the surface of Jupiter because we can't see it. So, clicker question number 1, which is open to answering now. What is the distance where temperatures were cool enough for water to freeze during the planet formation period?
Right?
Yes. Okay. All but one got the frost line. The frost line is the point where it was cool enough to form.
You didn't let me answer.
I would have if you. So the Kuiper belt. The Kuiper belt. What is the Kuiper belt?
There's asteroids there. It's around between the treasure planets and
It's not where the asteroids are. The asteroid belt is what you were saying, but it's further out. If you go out beyond Neptune, then you have a bunch of icy bodies like Pluto. And the Kuiper belt is those icy bodies that are out beyond the gas giants or the ice giants. So the Kuiper belt is out there further. They're definitely frozen objects, but the frost line is the separator between where the terrestrial planets are and where the Jovian planets are, because that's where it was cold enough to have condensation of water. And of course, what kind of objects do we find in the vicinity of the frost line? We find the asteroids that Max mentioned. The frost line is somewhere in that vicinity. Now, if we look at the shapes of the planets, we see something interesting. The planets are not as spherical as the Earth is.
Isn't the Earth like more X-shaped?
The Earth is a little bit fatter at the equator than it is the poles, just like me. But if you look there, the Earth is only, I think it was 0.3%. The radius of the equator is 0.3% larger than the radius at the pole for Earth. Pretty close to spherical, but it is oblate. Oblate means that you have stretched it out along the axis perpendicular to the rotation. I learned this as I was preparing for today's lecture. It is very, very commonly said in football that a football is an oblate spheroid. And I discovered today that is not correct. A football is a prolate spheroid. Prolate is if you stretch it along the axis. Oblate is you compress it along the axis. And so the Earth is just a little bit oblate because it's spinning, and inertia makes things on the equator, they want to go straight and have to be pulled in, but it ends up pulling them out just a little bit. What we typically call, a centrifuge effect. There's no such thing as centrifugal force, so I don't want to say the wrong words here. Jupiter, because it's not solid, it's gas. That gas is much more prone to being elongated because of the spinning. So Jupiter here, 71.492 versus 60.8. Okay, you can read the numbers. Apparently I can't. But if you compare those two numbers, that's a difference of, and I don't remember the percent. I think it was around, I can't remember the percent. We can calculate the eccentricity, and the eccentricity for Earth is like 0.08, I think. And the eccentricity for Jupiter, no, that's not right. I don't remember it. Crud. 0.33, though, roughly for Jupiter. 0 point something small for Earth. Maybe it was 0.8. I'm trying to remember the numbers. I was going to put them on here, but Google Drive let me down, and it wasn't working for me. I couldn't get it on here in time. So that's a first difference. Now, if we go to Saturn, not only is Saturn rotating quickly, we'll see in a few slides, the periods, the time to do a complete rotation for Saturn and Jupiter are in the ballpark of 10 hours. So if you were on Saturn or Jupiter, your day would only be 10 hours long. Also, something that we won't see until we talk about the sun, actually, that's when I introduce it. We have what we call differential rotation. If it's a gas, there's nothing that says that everything has to rotate at the same speed. If it's a solid, by virtue of being solid, everything's fixed in location with respect to everything else. Gas, that's not so. And so you actually have a different length of the day if you're at the equator compared to if you're at the pole for these gas planets, which is interesting. In the sun rotates faster at the equator and slower at the poles. I believe for the planets, they tend to rotate faster at the poles and slower at the equator. I didn't look it up today because it wasn't part of today's lecture. Okay, each of the planets has rings. You heard Russell talking about that beforehand. We always think of Saturn as having rings because Saturn has big icy rings. But in studying the other planets, it's been found that all of the gas giants have rings. It's just the rings around Jupiter and Uranus and Neptune are very thin, and they're made up of dark material. Things, well, it's like tarry or something like that. So made up of a different kind of substance. Now that brings up a question right here, not one that's on this slide or even in today's lecture, but where did the rings come from? How could all the planets have rings? You guys, you may not all be creationists, but creationists have lots of arguments for the Earth is younger than science says it is. And one of those arguments is about the rings, like the rings of Saturn. Our knowledge of physics says that those rings don't last very long. The rings of Saturn will be gone in a few 100,000 years. And so people say, well, the fact that we have them means that it couldn't be more than a few 100,000 years old. But scientists say, well, no, there must be something that causes the rings to occur and then go away. The same is true about comets. Comets only can live, a few hundred, I don't know, orbits around the sun before they're going to be evaporated. And so they say, well, the fact that we still have comets means that the Earth couldn't be older than the maximum number of times a comet can go around the sun before it's disintegrated. But scientists say, no. There's methods for creating the rings and methods for creating those comets. And they're both basically the same method. If you look at the rings around Saturn, they're made up of icy stuff. What kind of objects do we know that are made of icy stuff? Comets. And so the scientific theory on how Saturn got its rings is that you had a comet that came into Saturn. Because Saturn has a pretty large mass, it's about 100 times the mass of the Earth. Something gets close enough, Saturn pulls it in and won't let it go. And because Saturn has such a large mass, it has what we call a large tidal force. That is just the difference in force from one side to the other can become larger than the force of gravity holding the object together. And so gravity will shred an object if it's held together by gravity if you get closer than what's called the Roche limit. And so the theory is that a comet, or maybe more than one, came too close, got pulled inside the Roche limit, got shredded because of the gravitational forces of Saturn, and now we have the remnants of the comet orbiting Saturn. Now notice that there are gaps in Saturn's ring. We just had a homework problem that talked about the Kirkwood gaps in orbits around the sun. What caused those Kirkwood gaps? And that's what the whole problem was about. Orbital.
Jupiter pulled the
Okay.
object to it.
It was orbital resonance with Jupiter. If you had small integer ratios of the period of orbit of an asteroid with the period of the orbit of Jupiter, then you're going to have resonance kind of like you have something to swing. If you push them every time they come back, they're just going to swing bigger and bigger. If you push them every other time they come back, it's also going to get bigger and bigger and bigger. Well, the same thing occurs here. So we have moons And those moons will create places where there's orbital resonance with the moon that will clear it out. And so there's actually two different methods for this. One method is called shepherd moons, where you have moons that set up a stable band, and another one is just exactly like the Kirkwood gaps. So that's where we have the rings around Saturn. Well, what about the rings around Uranus? Where would they have come from? It's not icy, so where would that have come from if it's not icy, but more dirt and soil? For asteroids, right. So the theory is that the other planets, their rings, are remnants from an asteroid that got in too close, got inside that Roche limit, and the tidal forces shredded the asteroid apart and made the rings. And because they're just really thin, must have happened a long time ago, so most of it's been pulled in and now been assimilated. So that's the theory on where the rings came from. Why does it happen? Because they have a lot of mass and they can shred things. Now you can have moons inside of the Roche limit, but those moons have to be held together by something other than gravity. So like if you had a rock that melted and froze, it's actually bonded together, right? Rocks don't fall apart. And so those aren't going to get shredded by the tidal force. It would take a much bigger force to shred those. So you can have a moon that has been melted and frozen hold together. Okay, another thing here. Gas giants, all of them, generate more internal heat than they receive from the sun. What is that saying? That's saying that they're all having more heat leave than comes in from the sun. If you have more heat going out than coming in, what happens to your temperature? You get cooler. So all of them are still cooling. Why would they be hot? Okay, collisions from when they form, or more precisely, gravitational collapse. Because when things get pulled in by gravity, if I just take this and I drop it, it goes faster because of gravity acting on it. Well, temperature is a measurement. I'm not going to drop it because that would be a mess. Temperature is a measurement that's proportional to average kinetic energy, how fast they're moving. So if things fall in more, they're going faster, it's a higher temperature. And so for these big objects, there's a lot of infall, so a lot of thermal energy created. And there's nothing to sustain that temperature, so it's cooling, until eventually, of course, they'll, at some point, reach a stable temperature. And all of the gas giants have lots of moons. The number of moons goes up, every year. So I'm not going to ask you how many moons does it have. What are the moons like? Some of the moons are like the Earth's moons, and some of the moons are like Mars's moons. Some are big orbs, things like Titan and Triton and Io, Europa, Ganymede, and Callisto. And then, I suppose I should even go with Charon, but that's Pluto's. And then some of them, are just little objects out there that are basically asteroids. The colors, right? We notice the colors. Uranus and Neptune have these pretty blue colors, which is, you get your name Neptune because it looks something like the sea. Uranus apparently looks like Hades.
No, Uranus is the sky.
The sky, okay. The sky. That's better. The differences in the colors really has a lot to do with the temperature. They have similar, but not exactly the same gases. So like the difference in Uranus and Neptune's colors comes from just a slight difference in the amount of, I think it's carbon dioxide in the atmosphere. So we have ammonia and methane that condense at lower temperatures than water. And so as you get different temperatures, you're going to have different colors. So if we look, for instance, at Jupiter, I set it so it would show my motions better. I'm going to take that off because that's kind of annoying, isn't it? It's set for display to make it better. Okay, so if we look at Jupiter here, you see definitely different colors. Those different colors we now understand to be because of different temperatures. And those regions are called belts and zones. And so this here is a belt, if I recall correctly, which I am pretty sure I do. And this is a zone. What's the difference in them belts and zones? Well, it's pretty much like I wear a belt. And if I were to lift my shirt, which I won't do, you would see that where my belt is, there's a smaller radius, right? Same thing going on here. Where the belts are, you have a smaller radius. That is, you have material that's fallen down. It's cooler material, and that cooler material is the darker material. It's also lower, so it's not getting as much direct sunlight. So the belts, lower position and lower temperature. The zones are where it's bulging out. So you have hotter material rising up. And so that's what gives you the wider region. So we call this a belt zone circulation pattern. Those belts and zones, as we'll see, I think on the next slide, have winds whipping them about. Nope, not the next slide. It's coming up. Let's go ahead and do this clicker question and stay in sequence. Which statement is untrue? So all but one of these are correct. Which one is incorrect of these statements?
These are untrue. Okay, sorry.
Are we good to go?
Now we're good to go.
Now we're good to go. Okay. We had 1, 9, and 2. The correct answer. Amelia. Which one did you choose?
I chose B.
You chose B. And what was your reason?
Well, I knew for sure that they had rocks in the center. I wasn't sure if they'd been more deep than they received, and even just that they're all late. But I thought you said that if you keep going through the gas, it eventually becomes liquid, but it wasn't.
You're right. If you keep going, it eventually becomes, but you don't have a liquid surface. And indeed, all of your reasoning was pretty good there. We have rocks at the center of each, which I'll show you cut away in just a little bit. They all have more heat coming out than they receive from the sun, so they're all having more heat leaving, and they're all oblate. That means that they're fatter at the equators because they're rotating. Okay, some facts about Jupiter and Saturn here. Notice Earth is just here for comparison. This is the same pictures we started with. Jupiter is about 5 astronomical units away from the sun. How many times farther from the sun is Jupiter than the Earth? 5. Good. We're clear on what the astronomical unit means. It's 11 times the diameter of the Earth. So, clearly big. About 300 times the mass of the Earth. Very, very massive. It's over 70% of the non-solar mass in the solar system. Right? The sun is the large preponderance of mass in the solar system. But Jupiter is over 70% of what remains, and Saturn is most of what's left. So after these two, the amount of mass in the solar system that remains is minuscule. The Earth is a very little account compared to these. Excuse me. Notice the sizes of the two are not that different from each other. 9.5 times the Earth's diameter, 11 times the Earth's diameter is not that big a difference. But the masses are very different. So if you just look at those numbers, we can talk about the densities. Which one is going to be more dense? If they're roughly the same diameter, but one is 3 times the mass of the other, which one's more dense? Jupiter. Jupiter's more dense because it has much more mass for just a little bit bigger volume. So here's where the belts and the zones are introduced, and you can see I did identify them correctly there. The composition of gases, 90% hydrogen, 10% helium. So mostly hydrogen gas in the atmosphere. Trace amounts otherwise. How do we know these numbers? Well, we look at the spectra because the absorption spectrum of each gas is unique. And so scientists did that and they came up with, these ratios and some water. And then we got more specific. We sent the Galileo probe. I don't remember if Galileo was the name of the one that was actually the probe or if it was the orbiter, but it went into Jupiter and it was collecting data as it went into Jupiter. And of course, sending it back in real time to the orbiter to then relay to the Earth. And so as it went through, they had it measuring what types of gases it was going through. And they found that it had, like, for instance, less water than they expected. And then the scientists are all, wait, less water than we expected? How could we be wrong? Well, the truth is with astronomy, we find that we're wrong a lot. Remember the scientific method. You come up with a hypothesis to explain something interesting, right? First thing was the observation, then the hypothesis. And then you do experiments to test it. And if your experiment is confirmed, you have more confidence. If your experiment is disproven, then what do?
You try it again.
And
then you redo your hypothesis.
Yes, you reformulate your hypothesis because now you have more information. So you reformulate your hypothesis with this new information, and hopefully you now have a better hypothesis. And the process should lead you to more and more truth. But the more experiments you do, the more you're opening yourself up to disproving yourself. And so with astronomy, because we're so separated by things, we often find, nope, got that wrong. Well, let's tweak it. Keep tweaking until you get closer and closer to correct. So the temperature for the outer atmosphere is about 160 kelvins. Would you consider that hot or cold? No idea. No idea is an honest answer.
I'm going cold.
I'm going to go with you. Because room temperature, what would you say is room temperature? Use any units you're comfortable with. What's temperature in this room right now?
Probably around 70 degrees.
Around 70 degrees. I tried to keep it a little bit chillier than that. I was sweating like a felon this morning. I tried to keep it around 68, which is 20 degrees Celsius, which is 293 kelvins. So room temperature is somewhere in the ballpark of 293-ish kelvins. 160 kelvins, that's a lot colder. So that would be a very cold temperature by our standards on Earth. And it rotates once every 9.9 hours, which is why it's visibly flattened. You can tell that's not a sphere. That's oblate. It's eccentric with an eccentricity of, like I said, it's like 0.33 or 0.34. I'll put 0.34 here because I put 0.33 on the other slide. That way it'll be right on one of them. Okay, then if we look at Saturn, once again, this is Saturn without the rings. We look at Saturn. You see that Saturn also has, can you see that? Barely. It also has these belts and zones. Okay, that didn't work out very well. It also has, this will work. Things like that, the belts and zones. But they're not as clear. Why are they not as clear? The reason is on this slide, but maybe not where you expect. Not as clear because it's cooler. Also notice the percentage of gases is different than Jupiter's. Jupiter was 90% hydrogen, 10% helium. Saturn, 96% hydrogen, 4% helium. What's left? trace. Only trace amounts of other gases in both. And notice this one rotates once every 10.7 hours. A little bit longer than the 9.9 hours of Jupiter. But once again, that's a pretty short day, especially when you consider that these are big objects. Rotating a big object that quickly means that it's really whipping around the equator. Now we're going to talk about the weather here. By the way, it is the most oblate. That's not a tool I want. It's the most oblate of the planets. Saturn is. So, clicker question number 3. Now Tiami's back to the good. So approximately how much of both Jupiter and Saturn's atmosphere is composed of hydrogen and helium? Notice this is and, so it's hydrogen plus helium equals. Russell? Got to choose one. He's thinking. There we go. Okay. Here's what we got. Nobody said 50%. Nobody said 75%. 2 people said 90%. 3 people said 96%. And 7 people said 100%. So, talk to me, Jessica.
I put E.
Jessica put E. Why'd you choose E?
Because hydrogen and helium and Jupiter and Saturn equal.
Do you remember what the numbers were for Jupiter and Saturn?
90%, 10% in Jupiter. And then Saturn was 96% and 4%.
Right. So the 90 and 96, those were just the amounts of hydrogen. Now, of course, this is in the atmosphere. This is not talking about the entire planet. It's just in the atmosphere. But the atmospheres are essentially all hydrogen, helium. Trace amounts of other things like water, ammonia, methane. So what do we see when we look inside? Here's a cutaway of Jupiter. And the first thing you note is this out here looks like the crust on the Earth in the pictures, but it's not. What it is just the region where the clouds are getting dense enough for us to start seeing, hey, there's where the surface is. And as you go in, there is no clear distinction for change until you get down to here. Here's where you have the first distinct change. What happened as you went down is it got thicker and thicker. And so you start with an atmosphere that's mostly hydrogen. You go down, it gets thicker. There's more pressure, higher temperatures. You get a high enough pressure, and it was theorized that you could form a metallic form of hydrogen. Right? If you look at the periodic table back there, that first column is metals. And hydrogen's in the first column. So theoretically, hydrogen should be a metal. The problem is, it takes some pretty extreme situations to make hydrogen a metal. And just like mercury, now mercury is element what, 80? It's in the middle of what we call the transition metals. Mercury is a liquid metal at room temperature. You know, you watch the movies, they talk about, yes, it's a mercury switch. What's a mercury switch? Well, you have liquid mercury there, and if somebody jostles it, why, the mercury forms a bridge, and since it's a metal, it's conducting, and that's what sets off the bomb, right? Well, hydrogen should do the same thing. And so scientists worked until they finally, I don't know, maybe 10 years ago, were able to create liquid metallic hydrogen on Earth. And so then it went from being a theoretical prediction to, yes, it really does exist and can definitely exist here in the planets.
So hydrogen is a metal?
Hydrogen is a metal, yeah. Now, why did they think that it had to be metallic? Well, it's not on this slide, at least I don't think it is. But Jupiter has a very, very strong magnetic field. Well, to make a strong magnetic field, we needed a conducting liquid going around in circles with convection. And they're like, well, to make that very strong magnetic field, it's not going to be in there in the core. It's got to be something that's out there moving faster. And so they said, well, there must be something conducting out there, so it must be liquid metallic hydrogen. So that's really why I said it's got to have that liquid metallic hydrogen there. Now we feel a lot better because we've been able to actually make liquid metallic hydrogen. Actually, when you read up, you'll say some people question if we've been able to make it. But that's what is believed to be making the magnetic field. Yes?
Is there any guess on how hot it is at the core of Jupiter?
There is. I don't know the number. I mean, there usually is, right? You've got computer models. They'll tell you a number.
You know, if it's like somewhere in the ballpark of like comfortable temperatures.
No. It's extremely hot. You get down here and you finally get to where water would be. Why would water be down there near the core? Because it's more dense. Differentiation occurs really easily if you have a fluid, and water being more dense, it goes down. And so the water layer is there around the rock, and then you have that rock, which looks like a small rock when you look at the size of Jupiter. But then if you look at Earth, you do realize that that rock is bigger than this rock. So its rock is bigger than the Earth, but it's a small part of Jupiter. And it's going to be, I believe it's hotter, definitely much higher pressure than we have on Earth. So it's not something that we'd say, oh yeah, that looks like Earth too. So that's a cutaway look of Jupiter. What's this right here? Yeah, that's depicting Jupiter's ring. Oh shoot, I'm out of time. Someday I'll learn to lecture faster. When I start, I lecture really fast. If you look at the picture here for Saturn, it looks very much the same. So you learn about Venus or Jupiter, you learn about Saturn, and we will pick up here next class period.